Next, we summarize several key factors that influence game power consumption based on collected data. According to Perfetto's metric classification, we categorize power consumption into CPU, GPU, memory, display, and network. First, let's look at the GPU. We tested an online game under different graphics quality settings and observed a strong positive correlation between GPU clocks and GPU power consumption. The higher the GPU frequency, the higher the GPU power consumption, which aligns with intuitive expectations. When switching from smooth quality to higher quality settings, GPU clocks increase significantly, and both GPU power rails and total power consumption rise accordingly. This indicates that GPU pressure is often the most direct and sensitive power factor in graphics quality settings. The second important factor is bandwidth. In an empty scene with stacked transparent objects, 30 layers, we compared texture compression and Mipmap usage. We found that enabling Mipmap has an even greater impact on bandwidth and power consumption than texture compression alone. With Mipmap enabled 50 layers, bandwidth dropped from approximately 6 gigabytes per second to 1.5 gigabytes per second, and total power consumption was significantly reduced. We also observed that GPU clocks slightly decreased after enabling Mipmap. This indicates that bandwidth not only affects memory power directly, but also indirectly reduces GPU pressure. Therefore, for 3D rendering, it is strongly recommended to enable Mipmap for all textures. By fitting bandwidth and power data, we derived an empirical conclusion. For every additional 1 gigabytes per second of bandwidth, power consumption increases by approximately 60 to 70 milliwatts. This result is consistent in magnitude with the industry rule of thumb. 1 gigabytes per second bandwidth corresponds to roughly 100 milliwatts of power. Next, let's look at display-related power consumption. We tested different brightness levels, refresh rates, and screen content. The results show that higher brightness and higher refresh rates lead to higher display power consumption. Under identical conditions, 90 Hz consistently consumes more power than 60 Hz. An unexpected finding is that screen content itself also significantly affects display power consumption. For example, black screens and highly colorful screens exhibit a large power difference. In most games, display power consumption typically falls between 150 and 200 milliwatts. Values significantly above this range are worth further investigation. Next is network-related power consumption. During Wi-Fi or cellular downloads, network modules consume significantly more power, and CPU load also increases accordingly. In most games, network-related power consumption generally falls within the 100 to 200 milliwatt range. We also collected data from live games. If network power remains abnormally high during idle or low interaction states, it is necessary to check for unnecessary network activity. Finally, let's look at CPU. The most direct factor affecting CPU power consumption is operating frequency. We compared execution on the main thread and job system. Using gears, we observed that when heavy computation is concentrated on the main thread and big cores run at high frequency, overall power consumption increases significantly. After splitting computation into the job system, big core frequency drops and total power consumption decreases substantially. This is because CPU power consumption depends not only on frequency, but also on the square of supply voltage, leading to nonlinear power growth at high frequencies. Therefore, CPU optimization should avoid keeping big cores at sustained high frequencies and also examine whether child threads have abnormal time consumption ratios. In real-world cases, fixing an abnormal network-related worker thread reduced total power consumption by nearly 1 W. During SimplePerf usage, we also identified a common misconfiguration. In G-Online reports, two functions differed by nearly 10x in cost, but appeared almost identical in SimplePerf. This discrepancy was caused by packaging differences. GameOptim used a release build, while SimplePerf used a debug build to preserve symbol names. Further investigation showed that release builds can also preserve function symbols. After using IL2CPP release builds, SimplePerf results matched expectations. In summary, there is no single silver bullet for game power consumption optimization. GPU pressure, bandwidth, CPU frequency, display settings, and network behavior all have significant impact on total power consumption. Only through data-driven analysis can we accurately identify power bottlenecks and perform targeted optimization.